Welcome to the lesson 9 of industrial instrumentation. In this lesson, we will basically cover one of the most important temperature sensor, that is resistance temperature detector. Okay. Resistance temperature detector, even though it is not much used in the industry, in the plant you will find the thermocouple is huge in number, then you will find the thermistor, but I should say for precision thermometry, that means if I want to measure the temperature with high accuracy, resistance thermometer is the resistance temperature detector is the only solution, because this, even though it is resistance thermometer, nobody calls nowadays, we call it resistance temperature detector, and there are three basic classes of the resistance temperature detector. You will find we have platinum, then nickel, copper, tungsten. All these things will be discussed in details. Also the signal conditioning circuit of the resistance temperature detector, which are basically nothing but some bridges. Either you have seen BBS cases also, we can use it either in the unbalanced voltage mode, or you can use it as a balanced mode, right. So, let us look at the contents of this lesson. First, we will consider the theory of the resistance temperature detector. Then we will discuss the measuring bridges, what are the different measuring bridges in the resistance temperature detector. Then we will see the construction, what is the basic constructions of the resistance temperature detector. So, obviously, at the end of this lesson, the viewer will know details of platinum RTD, then its signal conditioning circuits, its construction. So, these are the basic materials, or the people will be familiar with. Most important is the circuits, which is not big, because from the user point of view, we will get this resistance temperature detector ready from the market, but we must know the how to use it, how to make our signal conditioning circuitry, so that the lead wire errors and other different possible errors can be minimized. Resistance thermometer theory, if I look at resistance thermometer, that is alternatively known as a resistance temperature detector or RTD, is one of the most accurate temperature sensors. You see, this immediately people will raise the question, that means why do you need such an accurate temperature measurements? In many industrial applications, this is not necessary. Even there is a temperature difference of 1 or 2 degree or 3 degree, it hardly matters. Especially at high temperature, suppose the temperature is around 100 degrees centigrade or 200 degrees centigrade, percentage error is quite small, and many processes you will find, suppose in a plant, in the process plant, this much of difference hardly matters. We do not need that accurate temperatures detectors, and resistance temperature detector is not very, it is a cumbersome, it is a little, circuits are complex and all those things are there, little lot of precautions you have to take, but there are some applications. One of the applications is the bioreactor application, that means where the cell, the bioreactor, the cell grows. So, in that type of situation, the temperature, precise control of the temperature is very important, right. In that type of situation, resistance temperature detector is the only solution, because in that type of situation, if the temperature varies, suppose if it is prescribed temperature or set point should be 31 degree centigrade, it should be 31 plus minus 0.5 degree centigrade, not more than that. Because if the temperature deviates above or below these, then the cell may die. So, in that type of situations, I need the precision resistance measurements, because once you make the measurement, in all instrumentation systems, once you make the measurements, I can control also the temperature. The need of measurement is to control it, is not it. That means heater power is to be controlled, or some boiler temperature is to be controlled, all those things will be there until unless we can measure it precisely. Moreover, you will find in some situations I need to measure this temperature, small temperature differences. In that type of situations also I need resistance temperature detector, because I need a high accurate temperature difference there, right. The variation of resistance of a metal with the temperature can be represented by the following relationship. Let us look at the relationship. It is R T equal to R naught 1 plus alpha T plus beta T square plus gamma T cube plus so on. This is equation number 1 of the resistance thermometry. This is the basic equations, right, where this R naught is the resistance at 0 degree centigrade, R T is the resistance at T degree centigrade, and alpha, beta, gamma etc., are constants, right. Now, the purity of the platinum can be checked by measuring this R100 by R0, because whatever the actually the materials you are using for making your resistance thermometry, that should be pure. Unfortunately, if it is not pure, then what will happen, you will see that it will deviate from the conventional resistance temperature graph. So, because alpha, beta, all things will change. So, I need a pure platinum. And moreover, you knew that one of the basic need of using the resistance thermometry is especially platinum resistance thermometry is its inertness. Platinum is very inert, and whenever you are, so that I can use it in very hostile environments where there is a chances of oxidations and all these things, that can be avoided in the case if you use a platinum thermometry, or it will not be react with any other. Suppose if I want to measure the temperature of the chlorine, or suppose if I want to measure the temperature of the sulfuric acid, okay, sulfuric acid bath, or sulfur, molten sulfur. So, that type of situations I need some thermometer which will not, even though we can put in a well or in a shield or in a sheath. So, it does not matter. So, it should not react with the materials of which we are interested to measure the temperature, right. So, purity is a one of thumb rule to check the purity. Once you get the resistance thermometers, you check its ratio, resistance at 100 degree centigrade and upon resistance at 0 degree centigrade. You measure it, and it should be higher. If it is higher than 1.390, it is better. We can approximate R T as R T equal to R naught 1 plus alpha t plus beta t square. R T equal to R naught 1 plus alpha t plus beta t square. This is equation number 2. For pure platinum, alpha equal to 3.94 into 10 to the power minus 3 per degree centigrade, and beta equal to minus 5.8 into 10 to the minus 7 per degree centigrade square. The equation is nonlinear. You see the equation 1 which we have discussed, we have seen, is a nonlinear equation. Obviously, if you take above alpha, if you take beta, gamma, it is nonlinear. But fortunately, you see the value of the beta here, whatever the beta value you are getting, beta equal to minus 5.8 to the minus 7. So, value of beta is quite small, right. And we can see that we can measure also the how much the nonlinearity. So, you can see for the most of the practical cases, that is the reason I am saying that however the nonlinearity of the platinum RTD we have calculated at 100 degree centigrade is 0.76% of the full scale deflection, right. It is quite small for the most of the applications, right. Now, to calculate these actual temperatures, we do not have to solve the quadratic equation. You see the two basic scientists, Callender and Griffith, worked a lot on the resistance thermometry. They suggested that instead of solving that quadratic equation, that means second order equations, because you see the most of the cases, if I take, even if I take nonlinearity, if I take up to the second order, that means R t equal to R naught 1 plus alpha t, that means like this one. If I take, let me take a blank page. So, okay, that is okay. So, if I take for the most of the practical purposes, sorry, if I take R t equal to R naught 1 plus alpha t plus beta t square, that will suffice. This is a t square, please note, okay, this will suffice, right. So, you can see that in this type of situations, or I can approximate like this, because higher terms like gamma and all these things will be quite small and can be neglected. So, amount of nonlinearity will be introduced by higher order terms will be very less. So, I can take it up to, if I take up to beta or t squares, it is more than whatever we need, or accuracy, as I told you, we have seen the 0.76% of the full scale. So, it is quite small. So, up to beta if you take, that means up to second order t square if I take, that is enough, right. So, instead the resistance temperature dilation is rewritten as R t equal to R naught multiplied by 1 plus C into T p t, this is equation number 3. where C is the mean temperature coefficient of resistance between 0 degree and 100 degree centigrade. When we define the platinum temperature TPT, which is nearly equal to the true temperature T by the relation TPT equal to RT minus R naught upon R100 minus R naught into 100. This is question number 4, where RT, R naught and R100 respectively denote the resistances at T degree centigrade, 0 degree centigrade and 100 degree centigrade respectively. The quantity R100 minus R naught is called the fundamental interval of the thermometer. The difference between the true temperature T and the platinum temperature TPT was accurately given by the parabolic formula as follows: T minus TPT equal to delta T by 100 whole square minus T by 100. This is equation number 5, where delta is the constant for that particular specimen of wire. Now, to derive the equation 5, we will proceed as follows. We have taken T minus TPT, T minus alpha T plus beta T square upon 100 alpha plus 100 square into beta into 100. This actually we got from equation 2 and 4, right. So, this can be equal to minus beta 100 square upon alpha plus 100 beta multiplied by T by 100 whole square minus T by 100. Thus, delta in equation 5 is given by delta equal to minus beta 100 whole square alpha plus 100 beta. The value of delta for the specimens employed lies between 1.488 or to 1.498. It should be 2.498. The higher the purity, larger is alpha and smaller is the delta. Now, obviously, delta I can find from the equation 5 by finding the platinum temperature TPT for the boiling point of sulfur, which is usually 444.6 degree centigrade. The reason that we have chosen the sulfur boiling point, because it is available in the pure form, and instead of taking at the boiling point of waters, we are taking little higher temperature. Usually, as you know that resistance thermometer can be used, especially the platinum resistance thermometer can be easily used up to the temperature of 650 degrees centigrade. So, we can take the temperature of 444.6 degrees centigrade, it is fixed for the normal temperature and pressure, whose true temperature is known, and then substituting equation 5 we can find it, right. The effective range of the RTD depends on the type of wire used. There are various, as I told you, there are 4 different types of RTD, and what are the ranges and how it will be effective can we look at from this table. Platinum, it is RTD, we have made in a table. It is a temperature range is 100 to 650 degree centigrade, good linearity and chemical inert. That is the most important thing for the platinum RTD. Its chemical inertness. You see here, this chemical inertness is the most important factor why the platinum is used repeatedly for making RTD, or I should say it is a de facto standard, industrial de facto standard to use the platinum RTD, even though we have the nickel and copper and all these things. Nickel I can go for minus 180 degree centigrade to 430 degree centigrade, and minus 200 degree centigrade to 60 degree centigrade, and nickel and copper are susceptible to corrosion and oxidation. This is the problem with the nickel and copper, but you can use it in some situation. You know, platinum is quite expensive also. If you use a large number of measurements, I can have to manage with the nickel and copper, and in that type of situations I have to use in a sheath material, or I have to put this entire RTD in a well, so that it will be protected from the environment, right. Or instead I can use a tungsten also, which is a rather newer, I should say, minus 270 degree centigrade to 1100 degree centigrade. So, now this is a figure 1, where you can see the typical resistance temperature characteristics of metals. You can see here we have plotted RT by R0 in y axis, temperature in the x axis. Obviously, at 0 degree centigrade RT by R0 will be 1. We have plotted the first one is of nickel, then you have plotted for copper, then you have plotted for platinum, then you have plotted for tungsten. You can see that the platinum sensitivity of the platinum is rather low, even though tungsten is even lower, but the tungsten advantage is we are getting the higher range. So, that means per degree centigrade change of temperature, the resistance change of the platinum is smaller than the copper and the nickel, right. Now, RTD circuits, how will I now actually what is the in RTD circuits, if the temperature changes, the resistance will change. So, somehow the other I have to measure that resistance change, right. So, the resistance change can be calibrated in terms of temperature. That is a very simple how we can make the measurements and how we can measure the measurement, how can you can make or how we can make convert this resistance change in temperature. That is our goal for making RTD circuits. Now, basically these RTD circuits are Wheatstone bridge circuits, right, because Wheatstone bridge is, as you know, it is a very at balance, it is very easy, we can find the unknown resistance with the help of another known resistance. So, it is always used for measurement of the unknown resistance, but please note the simple Wheatstone bridge you cannot use, we have to use some modified form of Wheatstone bridge, because RTD is a sensitive instrument, it is a contact resistance, all those things which we have to take care of, we have to count on that, right. Now, RTD can be connected in one arm of the Wheatstone bridge as shown in figure 2. You see this is a figure 2, a simple Wheatstone bridge circuit with RTD in one arm, right. You see this is our RT is RTD and these two fixed resistance R1 and R2, right, and this is our R3, this is a variable resistance. We will balance the bridge with the by varying R3. Okay. Either I can take the unbalanced voltage D and calibrate that unbalanced voltage in terms of temperature, or I can calibrate this R3 in terms of temperature. It can be, in that case it will be slide wire. Now, I am telling potentiometer, in that case it will be simple slide wire, where I can shift this. Okay. That means, it looks like this, a wire will be like this one and there is a contact, it will move like this one, right, and this length will be calibrated in terms of temperature, like a conventional potentiometer, okay, school level potentiometer. So, where I will have a graduated scale here. So, if I move this one, so I can balance it and this will be calibrated in terms of temperature, by which I can measure it, by measure any unknown temperature, right. And at balance, obviously, you know that it will be R2 by RT equal to R2 by R1 into R3. It is very simple, I should not draw it, and though it is a basic Wheatstone bridge. Anyway, for sake of completeness, I am drawing. Suppose I have a circuit like this one. So, we have R1, R2, this is our RT and this is our R3. We make RT variable and this is the potential. Suppose this point is A, this is B, this is C, this is D, and suppose this current is I1 and this current is I2. Right. So, you see that EAB will be equal to potential drop across this R2 into I2 and EAC will be I1 into R1. At balance, when there is no output at the detector, so I can say I1 by into R1 equal to I2 into R2, right. Similarly, on this side, because if balance, all the current will pass through this one, no current will flow through the detector. So, on this side I can write the EDB will be equal to I2 into RT and EDC equal to same current will flow. So, I1 will flow through this one, I1 into R3, right. So, I can write I1 into R3 equal to I2 into RT. So, if I divide this equation and this equation. So, I will get, suppose this equation, whatever the equation now, some 1 dash, suppose this is 2 dash. So, if I divide 2 dash by 1 dash, I will get R t by R 2 or multiplied by R 2 into R 3 by R 1. So, I can put R 1 here, okay, and put this in the graph like this. So, you see that if I take now R 2 and R 1, these two resistance R 2 and R 1 equal, then what will happen? You will see that this will cancel out. So, R t will be. So, in that case, if R 2 equal to R 1, so I can write that R t equal to R t equal to R 3, right. R t equal to R 3, fine. So, any change in so R 3 will give you at balance, I will balance the varying R 3. So, obviously, R 3 will give you the unknown temperature. So, R 3 should be calibrated in terms of temperature, fine. So, these are the balance equations I have written, R t equal to R 2 by R 1 into R 3. So, R 3 is an adjustable potentiometer. All resistors and potentiometers are made of manganese in order to avoid any effect due to ambient temperature change. You know, manganese has a lowest temperature coefficients of resistance. So, we always choose manganese to avoid any ambient temperature change, right. Potentiometer R 3 might be calibrated in terms of temperatures, and 3 improvements must be made in the simple Wheatstone bridge. There is some simple Wheatstone bridge you cannot use, some modification you have to need. Why you need these modifications, we will explain one by one. You see the contact resistance of the potentiometer R 3, if you remember the potentiometer, the bridge, basic bridge, the contact resistance of the potentiometer R 3 is directly in the bridge circuits, okay. And this contact resistance may vary from a fraction of ohm, but it is quite variable. Since it is in the bridge circuit, so depending on the contact, okay, your bridge balance equation will change. That is very undesirable properties, right. This is the number one problem. Now, another problem is RTD, you see that you cannot put the RTD very close to the point of measurements, right. I need certain amount of distance from the point of measurement, from where I will install the RTD, and there should be certain amount of distance where I will make the measurements, right. Even though nowadays all these intelligent sensors and all those things are coming where the transmitter itself are, because you have to if you want to make the unbalanced voltage as a if you want to calibrate this unbalanced voltage, as it happen in most of the control systems, that unbalanced voltage in terms of temperature. So, you have to convert that in the current domain, but certain length of wire is there, even though 1 feet of length or suppose 1 meter length of wire is necessary also. These are basically lead wires, because you cannot install the bridge itself on the sensor. So, bridge will be that Wheatstone bridge will be certain from might be 1 meter away from the actual sensor or actual bulb, I should say temperature thermometer bulb, right. So, there is a variations of temperature along the length of these lead wires. So, that will create the problem, right. Now, current through RTD causes a heating effect, which is variable depending on the magnitude of the current. The heat thus generated raises the temperature of the RTD sensor. Self heating effect, there is an R square R heat loss in the RTD because it is a resistance. There is an I square R heat loss in the RTD, obviously any resistance. So, and this self heat is called a self heating effect. You see, it cannot avoid it. This remains, okay. So, only thing you have to make a compromise between the sensitivity, and because I can reduce the supply voltage, as you reduce the excitation voltage or to the bridge, obviously what will happen, you will find the self heating error will be reduced, because you are reducing the current I in the bridge circuit. But if you reduce I, current I, what will happen, you know, you lose the sensitivity also, but that is not a big problem nowadays. We can easily make the signal conditionings, we can amplify the signals, okay. So, but we can avoid by this, by I can avoid the heat. You see, everything is, it is very simple. If I say that Okay, I am using a I will make this your self heating error very less. Okay, I will reduce the current. Okay, no problem, sensitivity will be reduced. But please remember, whenever you are using amplifier, okay, it has inherent noise. So, if we use amplifier, so that inherent noise will come in the picture also, right. And moreover, if you reduce the current, the unbalanced voltage will be not that small, not that large rather, to operate a V2I converter. V2I converter has some input voltage range. You have to raise the voltage up to that range. Only then the V2I converter. Because at the beginning of this course, we have seen that in all industrial applications, we do not transmit the voltage. We always transmit the current. So, even the V2I converter is necessary. If suppose 0 to 5 volt, if I say 0 to 10 volt, whatever it may be of your BJ excitation voltage. So, maximum output is 0 to 10 volts. In that type of situations, you know that the current will be 4 to 20 milliampere. If the BJ excitation voltage itself is very small, if I make purposefully to avoid the self heating error, so it may not work. So, you have to look at what should be the minimum BJ excitation voltage, right. The heating of the resistance due to the flow of current in it is called the self heating, right. The effect of the self heating is to make the reading erroneous, quite obvious. Therefore, the current through RTD must be low to avoid the self heating error. Now, usually RTD manufacturer provides the dissipation constant of the sensor. What is the dissipation constant? The dissipation constant is defined as the power required to raise the RTD temperature by 1 degree centigrade, right. Now, the self heating temperature rise can be found from the following expressions. Very simple, delta T equal to P by P d. What is this P? Delta T is the temperature rise because of the self heating in degree centigrade. P is the power dissipated in the RTD in watt, and P d is the dissipation constant of the RTD in watt per degree centigrade. This is a constant for particular RTD. Usually, the manufacturer will supply this value of the P d. Okay. Now, all thing will control the what is the minimum resolutions we can take the measurements, because you see if the P is fixed, if the P d is fixed, then delta T is fixed, right. So, in that sense I can control, I can reduce it, but I can which will control the self heating temperature error will control the resolutions of your instrument or resolution of your thermometer. Now, let us look at, as even though I discuss the self heating error, let us discuss the first problem in the conventional Wheatstone bridge, when I am using the bridge for measurements of temperature using RTD. Because we have seen in the conventional Wheatstone bridge, we have put the RTD in one arm of the bridge, and we put one arm of the bridge, and we will see that we are varying the other resistance to get the balance. And the problem I told at the beginning, that the contact resistance comes directly in the bridge circuit. So, depending on how much contacts you are getting, so it may vary. Suppose if even if it is changed to 1 to 2 or 3 ohm, so it will change your bridge balance equation, right, because I have to change the R3 again to make it get balance. So, this is quite erroneous, it is not undesirable, because contact resistance we are not, while we are calculating the bridge circuit, we are writing the Wheatstone bridge equations or bridge balance equations, we are not taking care of the contact resistance, right. So, that will make the circuits total erroneous, make our measurement total erroneous. Since it is a very precision instrument, so we have to take care of all these factors. So, this is a circuit, you see this RTD is connected to the bridge by a 3 wires. You see 3 wires means, you see here there is one wire, there is another wire, there is another wire. Now, interestingly you see this R3 now is no more in the bridge, R3 is in the bridge, but the contact resistance is not in the bridge circuit, it is in the galvanometer circuit or in the detector circuits. Ultimately, it is the galvanometers, or you can say it is just a multimeters or voltmeter, is not it, right. So, if there is little increase in contact resistance or little decrease in the contact resistance, nothing will happen. What it will do? It will simply make your bridge more sensitive or less, your detector more sensitive or less sensitive. Usually use it, is not it. Suppose in the case, some cases I want to use a milliammeter in a bridge circuit which is carrying a current of suppose 500 milliampere, even though our detector circuits can only read 10 milliampere. Usually we use a shunt, is not it, right. Use a shunt, and once I am very close to the measurements. So, I remove the shunt. So, that because I know that bridge is almost balanced, there is a little chance of passing a large current through the bridge through the detector. So, that type of situation will arises. So, any contact resistance will not, this contact resistance will no more in the bridge circuit. So, no calculation, nothing, whatever the bridge balance equation will write, that will be absolutely correct, but it will be in the detector circuit. So, it will make detector more sensitive or less sensitive, it does not matter, it is nowhere coming into picture. So, I am denoting some current because we have to calculate something. This I 2, which is the resistance, which is the current through the resistance R 2, I 4 is the current through the resistance R 4, and at balance this R 4 is I 4 is also flowing through R T, and since it is no current is flowing through detector in balance, and also this I 2 is full is flowing through the this R 3 as well as through R 1 back to the battery, right. This is called the RTD is connected to the bridge by the 3-wire method, right. Now, the potentiometer R 3 is placed in the detector circuit when it may lie in both arms of the bridge. The bridge is balanced by adjusting R 3. So, I am writing the equation I 4 R 4, if I look at the top one equal to I 2 R 2 plus 1 minus F into R 3. This is first equation of the bridge balance on the right hand side, or and also I can write I 4 R T I 2 R 1 plus F R 3. So, when F is a fraction of the potentiometer R 3 lying in the arm R 1 arms of the bridge, and I 1 and I 2 are the current to the corresponding arms of the bridge. Actually, it should be sorry, this will be I 2 and I 4, it will be I 2 and I 4 arms of the bridge. So, it will be I 4, I am sorry, this will be, if I take a, so this will be I 4 and I 2 are the current to the corresponding arms of the bridge circuits. That means, the current which is flowing through the R 4 is I 4, and current which is flowing to R 2 is I 2. Please note that I 4 is also flowing to the the resistance R T, that is bulb resistance of thermometer, and I 2 is also flowing to the resistance R 1 as well as R 3. Flowing to R 3, then to the, because at balance. So, detector is not drawing any current. So, at bridge balance equations we can write I R T equal to R 4 R 1 by R 3 plus F, if I take ratio R 2 by R 3 plus 1 minus F, right. F is a fraction of the potentiometers, R 3 lying in the R 1 arms of the bridge. So, obviously, in the R 2 arms the fraction of the potentiometer will be R 3 multiplied by 1 minus F, is not it, because on the R 1 arms it is F into R 1, that means, I should say like this one. If I like, that means, in the F R 3 will lie in the R 1 arms of the bridge, and 1 minus F into R 3 will lie, 1 minus F into R 3 will lie in the R 2 arms of the bridge, right, no problem. So, balance is obtained by adjusting the potentiometer R 3, which is calibrated in terms of temperature, no problem. So, the effect of the contact resistance is avoided, because the wiper of R 3 or jockey of R 3 is now not in the bridge, but in the detector circuit, which I told several times before, right. The only effect of the contact resistance is to cause a negligible change in the sensitivity of the detector, while the accuracy of the bridge circuit remains very high. This is the most important thing. 3-wire method is used to compensate for variable lead wire resistance. Okay. Now, the detector circuit connection is now made at the RTD and forms the lead wires, right. But you know the lead wires, even though lead wire resistance will remain in the case of 3-wire method. So, even though we contact resistance problem will be overcome, self heating error will be inherent, that will remain as it is, as well as lead wire errors will remain in the 3-wire method of RTD. Now, specification: each lead wire is made of copper wire of the same diameter and length, so that the each has equal resistance. These are specifications of the lead wires which will connect from the bulb of the thermometer to the bridge circuit, right. Because the lead looks like this, I have a thermometer bulb, okay, RT. This will be connected by bridge. Okay. So, this is our all lead wires. So, this is our lead wires, right. The 3 lead wires are run through the same cable, so that they have they have the same temperature condition. Okay. This is also necessary. If the resistance of each lead wire is R L, then the lead wire is in the RT arm of the bridge and one in the R4 arm of the bridge. Quite obviously, it is in the RT arm of the bridge and the R4 arm of the bridge. The resistance of the detector lead wire has negligible effect, because it is not coming in the picture. So, because it will make more sensitive or less sensitive to the detector circuit, because whatever the resistance in the detector, if it is high, so we can ignore that once we write the bridge balance equation. Clear? Now, these equations we rewrite the bridge balance equations for the 3-wire method when we am taking the length resistance of the lead wires, right. In effect, previously we have not considered the resistance of the lead wires, we assume that each lead wire has a resistance of RL. So, it will be I 4 R 4 plus RL equal to I 2 R 2 plus R 3 1 minus F. So, it will be I 4 R T plus RL equal to I 2 R 1 plus F R 3. If I take the ratios, R T plus RL, R 4 plus RL equal to R 1, if I divide on the right hand side by R 3, I will get R 1 by R 3, R 2 by R 3 1 minus F. Sorry. If the right side of the above equation is made unity, obviously, then what will get? I will get, if I R T equal to R 4, right. If the right side equation is unity, R T equal to R 4. Now, interestingly, when this right side of the equations will be equal or right side of the equations will be unity, only the cases when my potentiometer at the mean position, that means F is 0.5. Okay. So, only at that position of our bridge balance we will find that the lead wire resistance can be totally eliminated. So, whatever the temperature variation of the lead wires, we should not bother of, it is not coming in the bridge, but any other position of the our jockey or our slide wire or our potentiometer wiper, there will be the any other position than 50%, there will be error, right. Therefore, the balance of the bridge is independent of the lead wire resistance only at one particular setting of the potentiometer R 3. At one temperature of the scale, that is 50% of the compensation is exact and the resistance must be equal in magnitude. At other temperature, there is a slight and almost negligible lead wire errors when there is a changes of ambient temperature along the lead wires. Ultimately, these are, if there is a change in ambient temperatures along the lead wires, I want to compensate it. Okay. This is not possible for all position of the bridge balance, only at 50%, but that is very quite unobvious. I mean, it is quite funny. I mean, you cannot expect that the bridge will be always balanced at 50% of its position, right. F cannot be always 0.5, it can be any position. Now, Muller bridge or a 4-wire method is a method where using 4 lead wires, and the lead wire effect can be totally eliminated in this type of bridge, even though it is a cumbersome, but for precision thermometry this is the only alternative method, and we have to use it for making our circuit both your independent of the contact resistance, independent of the lead wire resistance, self heating error will remain as it is. The lead wire effect cannot be totally eliminated in the 3-wire method, because the compensation is not exact, at all positions of the potentiometer. However, the effect of lead wire resistance can be totally eliminated in the 4 wire resistance bulb method. Let us look at the method. Involves switching the resistance thermometer bulb lead from one arm of the bridge to the other arm of the bridge, right. We will see how it can be done. You see, this is our Muller bridge. Muller bridge is shown in figure 4. This is a figure 4. You can see this is our 4 lead wires, okay. And you see that potentiometer is RP2 and RP1. RP1 is the which we use to balance the bridge, and RP2 is actually purposefully it is not used once it is set. It is used to make the resistance of the right hand side of the bridge. That means, I want to make total R3, that means R3 total R3 like this one. That means, if I take that means I want to make this R3 and this R4 equal. That means, bridge resistance up to this it should be equal to resistance up to 3. Only then I can write the bridge balance equation. Only in that cases only the lead wire resistance will be totally eliminated, right. The excitations will find that what is the different connections and what is the bridge balance equations. In this case, we can totally eliminate our lead wire resistance problem. You see, it looks like this. RP2 is used to make R3 equal to R4 in position A of the switches. There are two different positions. Point 1 is connected to 2 dash, 2 is connected to 1 dash, and point 4 is connected to 5, right. So, these are the different contact points which will be modified in the case of, right. So, in that case you see the 4 is connected to 5, right. So, it is in the, and my bridge balance equations will be like this one. RP1A, that means at the switch position A, the value of RP1, these I am giving the name RP1A. What is that? Again I am repeating, it is the for the switch position A, that means all this connection, that means what are those connections? Connections are that I said that 1 is connected to 2 dash, 2 is connected to 1 dash, and 4 is connected to 5. In that situations, I will balance the bridge by varying the RP1, and suppose this new position is RP1A. So, RP1A equal to R2 plus R2 equal to RT plus R1, this is equation number 6. And in position B of the switches, we have changed the connections. We have changed the connection. Point 1 is connected to 1 dash, then 2 is connected to 2 dash, and 3 is connected to 5, right. So, the bridge balance equation is RP1B plus R1 equal to RT plus R2, right. This is our bridge balance equation. By adding equation 6 and 7, we get RT equal to RP1A plus RP1B divided by 2, RT equal to RP1A plus RP1B divided by 2, right. If I add, so obviously it will cancel out. We can see that the if I measure the bridge balance, if at the two position of the switches, if I can measure the value of RP1, that is RP1A and RP1B, I can totally and add and average it. So, I can totally eliminate the lead wire resistance. So, this is the beauty of the Muller bridge, but there are many precautions. You see that it is suggested that all the resistance should be in a thermostat except the RTD, so that it will equal resistance, and all the lead wires should be of equal length. If you can satisfy all these things, this is an excellent thermometry mankind has so far developed. Therefore, the measurement of the resistance RTD is independent of the lead wire resistance. Now, platinum, as you know, is universally used to make RTD for the following reasons. There are some advantages of the platinum, which is now de facto standard, I should say, of the platinum. Being a novel metal, it is used for precision resistance thermometry. That means, it does not, platinum is stable, that is another important thing. It resists corrosion, it has chemical inertness, and it is not readily oxidized. It is easily workable, or it can be drawn into fine wires, because it is ultimately to make the wires among the RTD, I have to draw it in wires. So, it is possible. So, this is another advantage of the RTD, why we use RTD, right. It has a high melting point of the platinum is quite high. it is obtained in high degree of purity. This is another advantage of the platinum. The impure platinums hardly will get, so you will always get the pure platinum, because if the impurity comes, obviously it is all this inertness, okay, stability, everything will go away. So, if it is available in the pure form, so it will retain all this original property, which is quite obvious. Now, these desirable and necessary features, however, do not come without effort. The resistance temperature relationship of platinum alters with the little impurity present in the platinum. This is another disadvantage, that means, if the little impurity is there, everything will be altered. Now, construction details of the platinum RTD bulb, you see here the construction details. It consists of a coil of fine wire wound on a notched mica cross frame. Okay, we will show that. The wire is arranged so that the good thermal conductivity is provided and a high rate of heat transfer is obtained. This is another thing is necessary, and the winding should be made in such a manner that the physical strain is negligible as the wire expands and contracts with the temperature changes. This is a typical problem, because you see RTD is a is not a semiconductor device or that type of thing. So, what will happen is a metal. So, if the temperature rises, the wire will be stretched, if temperature falls, wire will be contract in length. So, if the temperature rises already, so if already it is very tight manner, then what will happen? The strain will be developed. If the strain develops in the wire, then what will happen? It is, as you know, that we have in the strain gauges, this property is utilized to measure the strain, because if the resistance, if the wire is in tension, okay, so its resistance changes, right, which is undesirable, because we are not counting, what we want that our resistance change will be totally due to the change of temperature in the thermometer bulb only. That is the reason we have even did so much of work 3-wire 4-wire method to avoid the resistance temperature change due to the change of the lead wire. This is the number one thing. At the same time, we do not want that the change of resistance will be for any other factor. We want the change of resistance should be totally due to the change of temperature, not for any strain or anything, right. So, for that reason different atypical constructions will be available. So, we have to use that type of construction for making RTD. We can show here the construction details of platinum RTD bulb is shown in figure. You see, this is our typical construction details of the RTD. You can see here, this is our mica cross. You see, this is our mica cross, this is the mica cross, right. This is mica cross here, on which the RTD wire, it is wound on like this one in coil form, so that it will have a least amount of strain developed while the temperature rises. You have evacuated space, the mica crossing. This is another problem with this mica crossing. The mica crossing also limits the temperatures of the high temperature limit, even though it is hardly used above 650 degrees centigrade. And this is a platinum coil. Okay, this is our platinum coil. This is evacuated space, and whole thing is put in a stainless steel, so that it will be can prevent the any outside environment to react with the, even though RTD is quite inert, but in the case suppose we are using other type of nickel, copper or tungsten type of things. So, it should be protected from the environment, it should not react with the environment. Now, all this thing whenever using, you see one thing is very obvious, RTD is not for dynamic temperature measurements, that can be only utilized for, you can use it either thermocouple or thermistor is the best, because thermistor time constant is very small. We have seen that if you increase the time constant of the systems, once you put a RTD inside a sheath material like this one. So, what is the effect? It will increase the time constant of the system, that is also very undesirable, right. But for steady state temperature measurement, it does not matter. Suppose it will take some 2 minutes to come to the steady state condition, it hardly matters. One thing is quite obvious, whether you are using thermistor or RT does not matter. Once you use a you balance the breach. Okay. So, in that type of situation you cannot expect a large small time constant. There will be a time, some time is necessary to balance the breach. But if I use to for any dynamic measurement, suppose in the case of thermistor, I will take, instead of making the bridge balance, I will take the unbalanced voltage. Okay. So, that unbalanced voltage I will calibrate, I will convert in current domain and I will calibrate in terms of temperature. That is quite obvious, but in this case what will happen, that you see in the case of RTD, it does not matter. Okay. Even if you use a unbalanced voltage to make the measurements. Okay. So, what will happen, you see that this if you put inside a sheath, then what will happen, that your temperature, if your temperature changes. So, rapid temperature changes, I cannot measure it by this type of equipments. In that case, what I will do? I will simply use some other. So, it is not very used for dynamic measurements, it is used for steady state measurements or very slowly varying temperature measurements, right. For rapid measurements, in some situations, you see any process, you please note that the temperature measurements is not very very rapidly measured. In the case of bioreactor, suppose the temperature is very slowly measured, in that type of situations you will find that you need only few minutes. I mean, you sample the signal, you measure the signal, suppose every 6 degrees centigrade or every 10 degrees centigrade, not more than that, not more frequent than that. That is most of the cases suffice. But in some situations, say rapid temperature change is also necessary to shut off. Suppose very frequent temperature changes also measurement is necessary, especially where the safety problem is there, where you have to shut off the power supply or to the fuel supply to the boiler. So, that type of situations I need some rapid temperature measurement. So, and that type of situation, obviously people will not use RTD, right. Shut off means is basically any protection measurement means on off type of measurements. I have to shut off everything. So, that is on off type of measurements, and that time on off type of control. So, I do not need that precision measurements. Also, if it limits crosses, suppose some suppose 500 degrees centigrade, I have to shut off the power supply or fuel supply to the system. So, I have to stop the supply to the heating coil and all those things. That can be easily achieved with some other temperatures, so not for RTD. But RTD, as you know, it is very precision measurements, and the only problem is the self heating error. Other things can be easily resolved, like 4-wire and all these things, and it can be, that is nowadays very standard. Please note that is all RTD is used in the industry, is all RTD is to be used with the transmitter itself for all whatever the unbalanced voltage you are getting. So, for a standard RTD transmitter is there, that is utilized to make your measurement further. That means, it will convert that voltage, unbalanced voltage in the current domain, and that can be utilized to control, because that is to be again converted to the digital domain, because the signal which you will get in analog and that is to be fed to the computer through the data acquisition card, and the signal will come out of the data acquisition, convert in the current domain, okay, transmit again at the receiver side, you convert in the voltage domain, then you use it to some actuator, right. Some action is to be taken, and then the final control element, some valve is to be operated. So, this is all about your RTD, one of the most accurate temperature sensors.